First, we can, going back there, justify that expression. If H is commute, how do you convert the second term into, okay, let me justify, perhaps, instead of doing it in a sketchy manner, because it is physically very important, as I have mentioned. Therefore, you may wish to have a feeling about the way you can get it. Then you expand this for this special case that H is time dependent, but the H is at different times commute. If that is the case, how do you expand this expression into? You may need it for the perturbative cases, so let's do it in the reverse way. Let's try to expand this and let's see how it goes. I t to 0 dt prime ht prime plus 1 over 2 factorial minus I over h bar squared dt prime t0 t h t prime squared, right? Naively. Isn't that the way that you can write, expand this exponential? 1 plus x squared divided by 2 factorial, x cubed divided by 3 factorial, etc. So what is this? This is dt prime t0 t ht prime times t0 t dt double prime ht double prime. So all you have to remember is that the difference between that and a time-dependent and non-commuting case is there is the time ordering forced upon you. Here there is no time ordering. Then you can change this to the following. dt prime without any ordering problem. ht prime and ht double prime if you want. If you want to make analogy with the previous case, you don't have to. This way of writing is nice, right? Once you know what that integral is, you take the square of it and the cube of it and the blah blah. And this way of writing enables you to combine into it from there. The limits are not ordered. Limits are always t0 to t. I think that is sufficient for justifying this particular form. And finally, the most general non-commuting case, and we know, we have written down the answer previously, so there is not much left for us to discuss any further there. Okay. Now we move into the energy eigenvalue problem and energy eigenkets. Let's consider the following situation. Our main, perhaps I have to start with the following question. We have found the time evolution operator, which is really a formal solution to the so-called equation of motion, if you want, Schrödinger equation of motion. Then once you have it ready, then you have to act on any arbitrary state to get the evolved version of that arbitrary state. But usually in the quantum mechanical framework, we always express the arbitrary states in terms of a base set. Base sets are the favorite base sets, and at least for the space-related problems, are the eigenvectors of the position operator, eigenvectors of the momentum operator, or for the discrete cases, eigenvectors of the components of the spin, etc. But let's discuss the more a generic case of, suppose we have an operator A whose eigenvalues equation are defined as such. Capital letter is for the operator and little, small letters are the eigenvalues and eigencats. And this, of course, are complete and orthonormal, the space, being the eigenvectors of a Hermitian operator. So it's a good base, right? If this observable commutes with the Hamiltonian, then these two, A and H, will have a common set of eigenvectors, will have simultaneous eigenvectors. That's the general theorems that we have proven before, right? Well, if this set now, this simultaneous set is this one, if you want, that is, perhaps even all of the eigenvectors of A may be simultaneous eigenvectors of the H. Therefore, we can now define the following equation. The action of H on these eigenvectors will produce this. That is the definition of being simultaneous eigenvectors of both H and A, right? Because A is defined, directly they are defined in terms of the A, and using that commutation relation, we say these are also eigenvectors of the H. Of course, eigenvalues differ. Eigenvectors are common. They have different energy values associated with this. Then let's take advantage of this situation, and let's try to write our ultimate aim as I can. Let me repeat. The action of the time evolution operator on an arbitrary state. As arbitrary states are expanded in terms of bases, complete orthonormal eigenvectors of some operator. Therefore, I would like to know the effect of the evolution operator on the bases first. If I can work out the effect of the time evolution operator on the basis set, then it automatically yields me the result that I'm looking for. So, yes, psi of t in arbitrary state now can be expanded in terms of this, and I would like to know what is the effect of u on that. If so, u on psi of t will be reduced to the effect of u on A. Okay. Obviously, this is the evolved A. Oh, that's not a good way of writing, I'm sorry. Well, okay, perhaps symbolically. I haven't deciphered all the details. Any state at any time, T0 or what, they can be expanded in terms of a basis set. If you are interested of relating the coefficients of the expansion at t equals 0 and at t, and those type of things will follow from this discussion. So there is nothing wrong with that representation, although it's not fully detailed, really. So I'm interested in really this. And what is the effect of the u on A? To work it out, we do the following. In the case of time-independent H, let me deal with this. Time-independent because it's easier in this case, because it is a simple exponential, right, if it is time-independent. So what is the u? u is u of t0. Yeah, I keep it as general as possible. Minus I over h bar h t minus t0. Then I do the following trick. Let me insert completeness sums to the right and left of this. That is, A and A, sum over all A, and they're the primed ones. A prime, and A prime. Okay, so what is the expression that I get? The expression that I get is the following. Sum over A and A prime. A prime here, A prime e to the minus I over h bar t minus t0, A and A. This type of representation it will be very it's going to be more transparent when we work out, for example, this in the context of position eigenvectors, and it's going to be the Feynman's pulse integral version, really. But here it is more or less abstract, right? There are not much detail in here. So let's bear with me now. It is this expression that we get. So what is this? This I can work out. Notice that A is chosen to be an operator commuting with the Hamiltonian, and little a are its eigenvectors. Therefore, A and H have common eigenvectors, and A cats are also eigencats of the Hamiltonian operator. So this acts on here gives you e to the minus I over h bar Ea t minus t0 A. Then this becomes a number. You move the number out. E to the minus I over h bar Ea t minus t0 A prime and A. Use the normalization. Now I'm tacitly assuming that it's a discrete spectrum. If it is continuous, doesn't matter, right? As in the X or P case. Then you carry out one of the summation, and you have A e to the minus I over h bar Ea t minus t0 A and A. So this is the operator itself. The time evolution operator, we have found a representation of it if you want. T and T0, it is written in such a form. If you want this, you may remember that this is the projection operator along the A, right? So you have to really, in this way, you have written the time evolution operator as some exponential factors involving the associated energy eigenvalues and the projectors along the A. So it's a very wonderful, really, representation which could be used for many purposes. Now, we have this expression. Perhaps then we can proceed to see how does it act on an arbitrary psi. We have the projectors, therefore. Psi of t is u t0 psi of t0. If I expand it now, I'm using more rigorous language. if we have at t equals t0, usually, more often than not, this t0 will be chosen to be 0 because there's no, instead of carrying an additional phase factor all the way. But let's keep t0, and at the back of our mind, we know that it's going to be set 0. So this, suppose this initially expanded in terms of this, and I worked out what I know what this operator is in the A basis. So it moves in CA U I H T minus T0 A, and remembering that this is the projector we have worked out, EA T minus T0 PA A. So what do we get? We get the following expression: A CA e to the minus IH bar EA T minus T0 A. Notice that from this initial state expanded in terms of A basis to the evolved state again expanded in terms of the A basis. The only difference is that the coefficients originally taken to be constants become time dependent, and the time dependence is through these beautiful phase factors, right? So eventually, in the case of H, time independent H, that's valid. So this is very suggestive in the following sense. That will enable me to define the so-called stationary states. Let me see. What if special case 1, if psi of t0 equals 0, that's we are choosing 0, is chosen to be A, which is a member of this entire collection, a single eigenvector, a specific single eigenvector of the A operator, then the evolution will be what evolution will be? Just this one, e to the minus I over h bar EA t, as I have chosen the t0 equals 0A. It's a single one. This operator comes and acts on it, picks the EA because H and A commute. Then you have a pure phase. What is the probability of finding this evolved state in a state other than the A? For instance, question, what is the probability, say, for this evolved one? If I take A prime different than A, of course. A prime and A, which is 0, right? If A prime is different than A. What do I get? I get a very important result. If it is a given specific eigenvector of the A, then as it evolves under H, it stays in the same state. It remains in the same state. If originally in a specific one, in a specific eigenvector, eigenket, stays there forever under any influence, remains or stays or remains there always. Cannot go out because the only extra factor is this phase number. It cannot make any transition. So it is a pure state, single state. What about the how do you say? Okay, let me follow the book. Okay, before moving into non-stationary states, let me proceed a little bit with these states, and these are called the stationary states, right? Why? Well, let me demonstrate why. Stationary states sometimes this discussion and certain books are not that clear, so I invite you to really pay attention to this one. So when we have single eigenvectors, we started with h and a equals 0, and the eigenvector problem of eigenvalue problem of a is such. This is complete and orthogonal, and because of this commutation, h also acts on it and gives you the following eigenvalue equation. So this basis vectors are common eigenvectors of both h and a. Question: if you have another operator b, not necessarily commuting with a, consider another operator, another b, with ba not commuting. Not necessarily. It may commute or not, but let's keep the general discussion as general as possible. Now, start with the following initial state, A, and evolve to e to the minus I over h bar ht A. You have a time-dependent now state, right? Psi of t. For this particular state, what is the expectation value of this b, an outsider really, something which you brought in, has nothing to do with neither h or a. So what is the expectation value of this b in this psi of t? Well, if you work it out, what is this? This is e to the minus I over h bar ea ta, and this one is also ea plus I over h bar ea and t, bra and cat. Therefore, these numbers cancel and you have a, b, and a. The initial state before the evolution. So that shows that these states are stationary, really. That is, those states which are the time evolved versions of given specific eigenvectors, common eigenvectors of a given operator A and H, then those states are called stationary states because the expectation value of any operator in that state are time independent. Expectation values are time independent in here. That's why we call them stationary states. They depend on time explicitly, but expectation values are time independent. That's the definition of time dependence. This was valid for a single eigenvector evolved in time. What about the superposition of these eigenvectors? Now, this time consider psi psi t 0 of 0 to be CAA, an arbitrary superposition. Okay. What are the time-evolved version of this? Psi of t is u t0 on psi of t0. Let me use shorthand. Then this will be Ca e to the minus I over h bar EAT and A. That is the expansion of this originally superposed state. And it's a superposition again, but this time coefficients involve phases, oscillatory phases. Now if I take this state and compute the expectation value of that B, which I have dealt with in the previous case, what is it, for instance? Psi t, B psi t is A prime and A, Ca star prime, Ca e to the minus I over h bar Ea minus Ea prime t A prime B A. Unless B commutes with A, therefore they also, the A basis which I have been using is a common eigenstate of the B, this will be time dependent because this doesn't vanish because B doesn't necessarily commute with the A, therefore A vectors are not eigenvectors of the B, so this doesn't vanish. If this doesn't vanish, then these factors, time-dependent factors, are there, so it is not a stationary state. Despite the fact that individual members of a complete eigenvector basis, they form stationary states under the time evolution, despite the fact that they depend on time explicitly, but their linear superpositions are not stationary states. So this is not a stationary state. These are not stationary states. I will illustrate this. This is a very important point. Are not stationary states. A very important problem. Now that takes me to the interesting physics, which offers a good arena for illustrating most of these general theorems that we have developed. It is the spin precession problem. Spin precession. Well, if you have a magnetic field, let's take it to be constant and homogeneous. No, do we have to? No, we don't have to. Eventually we will do so, but uniform, static uniform. Yeah, let's do it that way. Static and uniform. As I said, we'll see more complicated versions of it, but to start with, to set the stage, this B is static, doesn't change in time. Uniform doesn't change in space. Let's take the direction defined by this as the Z, because external fields define directions for us. So what is the Hamiltonian? If this is at rest, it doesn't move in orbital, it doesn't make an orbital motion. Therefore, the Hamiltonian will be, the sole Hamiltonian will be just the interaction energy of this magnetic moment. So if it is an electron, yes, let's take it to be an electron. then mu is minus, e.g. this being now the positive quantity, I differ from the book, I put minus sign and this now is a number, positive number, 2mc s. G for the electron is 2, it's a point-like structure, as is demonstrated by the Dirac equation rigorously and experimentally, the observed value. So if it is 2, 2's cancel, then so you have a E over mc b dot s. Well, b is in this, we have chosen the direction of b as the z, so it is eb mc sc. So this is our Hamiltonian really for this configuration. For a constant homogeneous or constant static uniform thing, the Hamiltonian is proportional to the SC, and there is a factor multiplying it, and he defines this as the omega. He calls this a name. So Hamiltonian is simply omega, some number depending on the external magnetic field times the SC. Okay. Then, what is the time evolution operator? Time evolution operator then, this constant is, this coefficient omega is constant, therefore H is time independent. Okay, that's the point. Time independent. It could be time dependent, keeping the direction fixed. Its strength may change and we would have the second case. Again, exponentiated, summed. However, it wasn't just simple numbers, it was the line integral of h involved. Anyway, let's keep this as such, time independent. Then the time evolution operator, choosing the original time to be 0, you start your chronometer, not an arbitrary time, but at 0. The time evolution operator then is e to the minus I over h bar ht, which is e to the minus I h over h bar, so it is omega over h bar, right? Omega over h bar and t, sc. Okay, so we have found what the time evolution operator is. Then we have to consider an initial state. For the initial states, we could choose any bases, Sx, Sy, Sc, 3 components, so they satisfy an interesting, beautiful algebra. But any one of them have eigenvector basis. We could choose any of them as the basis. He says that the initial, we can take the initial state in terms of the z bases. Choose the initial state. Choose psi of t0 as a linear superposition of c plus t z, c minus z. So we choose these bases to start with, associated with the SC. I define these, let me write it here, plus minus h bar over 2 plus minus z is the definition of my basis set, which I have introduced in here, okay. Then, what will be the time evolved state? How does it evolve now? Under the influence of this u, psi of t is u psi of t equals 0, which is e to the minus I omega t over h bar sz c plus z c minus c. Scx on the plus z gives you h bar over 2, and on the minus z gives you, using the eigenvalue equations, which I defined in there. So what you have, c plus e to the minus I omega t over 2 plus z plus c minus e to the plus omega t over 2 minus z. So that's my evolved, my future state. This was my initial state and this is my future state. Notice that it picked Again, I have retained the original basis set. Now the coefficients are, the square, mod square of these coefficients are the ones which give me, for example, what is the probability of finding in this evolved state the up spin? Let's find that. What is the up spin? Probability of finding in plus z state, for instance, the evolved one, right? I haven't specified the initials yet. And for example, I can choose C1, C plus to be 1, C minus to be 0, or vice versa, or keep it as general as possible, normalize each of them as 1 over. Anyway, this will be plus z psi of t squared. So what is the plus z on this psi of t? It is this coefficient, right? C I plus I omega t over 2. Or this one minus z psi of t squared is, and writing, now this is projecting this on there, it picks this one, c minus e to the plus, sorry, omega t over 2 squared, c minus squared. Question, what is the probability of finding this one in the initial state? It is the c plus squared. Lesson, as far as probabilities are concerned, it didn't change. Whatever the original value of finding a plus, this is just whatever original value of c plus, it is the final value of c plus. Why is that so? Because I used the z basis and my time evolution operator involved sc, therefore it leads to this result. I have to change the now question to a slightly different one to make it more interesting. By the way, to finish this, what if I could have chosen c plus equal to 1, c minus equal to 0 to start with, if these are the initial conditions. Initial conditions. This is interesting, although some of you may think it's trivial. If the initial conditions are such, what was my initial state then? Let me write it explicitly so that you can see it. My initial state with these choices was plus z, really. A single state. It evolves what? How it does evolve? It evolves as follows: omega t, omega over h bar tz, so it becomes e to the h bar over 2 cancels, so minus I t over 2 plus z. So for this specific configuration, if my initial one was a upspin state, under this Hamiltonian, due to external magnetic field, it evolved to this one. So what is the probability of finding the minus in here? You see how beautiful it looks, this time evolution in here. 0. It means it remains in the upspin state, even under the influence of this Hamiltonian. So it's a stationary state. Under this driving of this Hamiltonian, this single state stays to be so there is no transition possible. And the probability of remaining the same is 1, and making a transition is 0. Now, if I reverse the question, suppose this initial condition, let me change the initial conditions. Hamiltonian is the same, configuration is the same, time evolution is the same, but I change my initial conditions. You'll see something beautiful coming out. Initial condition now. This is the first initial set of initial conditions. Initial condition, second set. Initial state, let me take the initial state to be plus x, for instance. Can I? Of course. I'm free to choose the initial state to be any way I like. It is the up spin state of the x. Initially, I have oriented my spin in the x direction, to be precise. How does it evolve now? Psi t equals 0 is plus x. Well, it's so beautiful that there are three different sets of bases, eigenvectors of SC, Sx, or Sy. These are the eigenvectors of Sx. They all can be expressed in terms of the others. What is this? This is 1 over square root of 2 plus z minus z. We worked it out, remember? The Sx eigenstates can be expressed in terms of the z's and vice versa, etc. If I was dealing with the minus x, this would be a minus. But let me carry over this discussion. Continue with this discussion. What is the evolved one? Evolved psi t is e to the minus I over h bar. My Hamiltonian is here. Omega t sc plus x, or that's the thing really. 1 over square root of 2 e to the minus I over h bar omega t sz plus z and minus z, right? I have expressed the plus x in terms of the z components because these z vectors are the eigenvectors of the SC. I know its action now. Okay, its action then becomes 1 over square root of 2 e to the minus I over h bar is gone, I omega t over 2 plus z e to the plus I omega t over 2 minus z. How nice. It is the new state now. You can ask several questions. What is the probability if this is the initial condition? What is the probability of finding this in plus z or minus z, plus x or minus x? Private homework. You ask those questions to yourselves. Probabilities of finding plus z or minus z or plus x or minus x in this. Well, you may enjoy yourself in the following manner. You can try to go back. As you have started with the plus x, you would like to see what is the plus x or minus x appearing in here. You reverse these. Write these z bases in terms of the x bases. This one is 1 over square root of 2 plus x minus x. And this one is 1 over square root of 2 plus x minus x. Recombine. If you recombine 1/2 e to the plus x e to the I omega t over 2 plus e to the minus I omega t over 2. How nice. Minus x. If it is minus x, this is e to the minus I omega t over 2 minus e to the plus I omega t over 2. To cut the long story short now, these are the small brackets. This is the large bracket. The first one is twice cosine omega t over 2. Second one is minus 2i sine omega t over 2. So I will write it here because it's the last thing that I would like to write. Let me write it clearly. So what it becomes then, psi of t becomes 2's cancel, plus x cosine omega t minus I minus x sine omega t. We have initial state was plus x. You see what's going on. If it was an initial z eigenstate and the Hamiltonian was around involving SC, it didn't change. It was a stationary state. But if the initial state for the same Hamiltonian is chosen to be an eigenstate plus x, it's a superposition, so it's not a stationary state. It's not a stationary state. Therefore, it evolved into this. There is the plus x and the minus x. It didn't stay in the plus x origin as it was. It developed a component minus x. This magnetic field in the z direction rotated the spin, aligned it, and gave you two possible combinations of plus x and minus x. So it is a beautiful game, really. We are going to continue along these lines anyway, so I better stop here. As I said, we will continue along these lines. This is a good point to stop.